All right, for our final DFT example that we're going to work with in Matlab, we are going to talk about resolution and zero padding. In the Matlab script that we'll take a look at, we're going to deal with two different sinusoid signals. One will be at 500 hertz, the other will be at 550 hertz. And we'll see that when we don't have a lot of samples, our resolution in the frequency domain makes it impossible to resolve those two frequencies because they're too close together. However, as we increase the amount of data, our resolution in the frequency domain gets better, and we are able to resolve those two signals even though they might be closely spaced in frequency. We'll also play games with zero padding, adding on zeros to get more samples in the frequency domain. Obviously, adding zeros doesn't improve resolution, but it's also still something that's useful to do. So we'll work through a handful of examples here in Matlab in just a second.
All right, so let's take a look at another Matlab example of computing the DFT of a signal. In this script right here, I already have kind of a handful of what I think of as interesting cases set up here. We're going to go through them by just changing the case index. What's happening in each one of these cases is I'm setting up a continuous time signal with either one or two sinusoids. So these parameters right here control the amplitude and frequency of the first sinusoid, and these parameters here control the amplitude and frequency of the second sinusoid. In these first 5 cases, since the amplitude 2 is 0, there's actually only one sinusoid on. So these first 5 cases are really the one sinusoid case. And then when we get to cases 6 through 9, we will take a look at the case where there are two sinusoids present. So you can see I turned on the second sinusoid. The other important parameters in each one of these cases are the number of samples that we're taking. So n controls the number of samples that I'm taking from the signal. And FFT length is the number of, really this controls the zero padding that's going on. So when the FFT length is equal to n, so here n is 64, the FFT length is 64, I'm not doing any zero padding at all. When n is 64, but the FFT length is 4 times n, then I'm actually padding on quite a bit of zeros to improve the number of samples that I get in the frequency domain. So as we work through these different cases, you can see the number of samples I'm actually taking is changing, as well as how much zero padding is changing. Down here in the kind of the guts of the code, you can see what I'm doing. I'm actually taking samples of the sinusoid. So my sampling rate is 8,000 samples per second. This is my corresponding time vector, which gets sampled at the rate fs, and n controls how many samples I take. So when I query this sinusoid, I will get n total samples. And then right here on line 52, to compute the DFT, instead of doing the double for loop like we've been doing in the previous examples, I'm just going to go ahead and use the FFT. The other videos in this playlist talk about the FFT and how we can use the FFT to efficiently compute the DFT. So here I'm just using the FFT as an easy way of getting out the DFT. And then after that, all I'm doing is plotting the amplitude spectrum. So let's go ahead and run this first case. Let's go ahead and run that and see what we see. So in this first case, since I only have one sinusoid, what I would expect to see is an impulse at the frequency 500 hertz that corresponds to this sinusoid term right here. Remember, in this first case, this other sinusoid is off. So let's see what I see. So what I actually see is the blue. Let me go ahead and delete this red line for now. The output of my FFT is actually this blue curve right here. And if I zoom in, I can see that it looks like I have a value right there at 500 hertz, like I would think, and I have almost zeros everywhere else. Let me rerun this one more time and leave that red curve back. According to the theory that I should see, what I should actually see here is this red curve. Remember, if I have an infinitely long sinusoid, that's an impulse in the frequency domain. But once I time limit it, that actually turns into kind of a rectangularly windowed sinusoid, which gives us a sinc function in the frequency domain. So this theory curve that I've plotted here in this first case tells me what I should be seeing, and that is what I'm seeing. Remember, the FFT or DFT gives me samples of the underlying curve. So these blue dots are right on the red curve like I expect, What's interesting though is I've kind of gotten unlucky in that my samples out here are what we call on picket, in that they are exactly sampling the zeros of the sinc function. So while I expected to see this red sinc function come out, because of I'm sampling on picket, I only see these zeros, and I'm not really sampling this red curve very well at all. Well, we know how to handle that. We know that if we do zero padding, I won't change the resolution of this curve. The width of this red curve will stay the same, but I'll get more blue dots on top of the red curve. So let's go ahead and go to case 2, which is the exact same number of samples, but I'm now doing quite a bit of zero padding. So let's see that. And now we can see that I am getting samples on top of that sinc function like I'd expect. And if I want to go to case 3, which is even more zero padding, I can get even more samples of that underlying sinc function. Okay, so these first 3 cases, the same number of actual time domain samples, which means the width or resolution of the sinc stayed the same, but my zero padding was changing to give me more samples. Let's go to case 4. Case 4 now, I go from 64 samples to 256 samples. So I've quadrupled the number of values that I'm taking on my signal, which means the width of this sinc function should get 4 times as small. So let's go ahead and take a look at that. And that's indeed what happened. Look how much narrower this sinc function is. Now it's still a sinc function. If I zoom in here, I can still see the sinc, but its width is much smaller. I have much better resolution in the frequency domain. This final case, case 5, keeps that number the same, but we're going to go to 4 times more for a total of 16 times over sampling. So now I can really clearly see this very narrow sinc function in the frequency domain. All right, so all that was pretty interesting. That gives us a feel for how the number of samples that we take and how zero padding changes things. Real samples control the resolution. Zero padding controls how many values I get on that underlying sinc function. Case 6 is the first time where I'll actually have that second sinusoid. I'm finally going to turn on the amplitude of the second sinusoid. So let's go ahead and run this kind of baseline case, which really is exactly like this case. N is 64. I'm not doing any oversampling or zero padding, but now I have 2 sinusoids present. So in my mind, what I would expect to happen is I should see kind of 2 kind of peaks, one corresponding to 500 hertz and the other corresponding to 550 hertz. Let's run that and see what we see. Well, this is what we see. So I've completely skipped over the frequency domain location of that other sinusoid. I need more samples in here so I don't skip over it. You can tell something interesting is going on because this value right here is much higher than this value right here, which kind of indicates there might be something here that I skipped over that's kind of boosting the signal content at this sample. So let's see if we can figure that out. Let me go ahead and grab more data to improve my resolution in the frequency domain. Let's go to case 7 here where I have a little bit more data. See what that looks like. And now you can see a little bit better what's going on. I have much better resolution in the frequency domain. I'm still getting my sample here at 500, but now I have some samples over here in the vicinity of 550 hertz where my other sinusoid is located. Now looking at this, this still isn't great because if I had to guess, I would have said there was a signal here and a signal here at 563 hertz. Well, it's not at 563 hertz. Again, I've kind of skipped over the bin location of where that other sinusoid is, so I can't really tell where it is real well. On case 8, let's keep our samples the same, so our resolution stays the same, but let's crank up the zero padding. So let's get more points on our curve, and now we're starting to see even better what's going on. I can start pulling those out a little bit better. I'm sorry, case 8. So let's go to case 8 and get some more zero padding. There we go. So now I can really start seeing what's going on. I zoom in here. I have a lot of samples around this 500 hertz and a lot of samples around 550. I can really start to see those 2 sinks popping out. If I really want to see them though, I should increase and improve the resolution. So if I have the ability to actually grab more real values of the signal, we should do that. So here in this final case, case 9, I actually grabbed kind of the most real samples I've ever grabbed, and I'm also going to do 4 times zero padding. So let's see what that looks like. And now that looks really good because now I have very good resolution in the frequency domain, The width of this is very small, right? The total width of this thing is just a couple hertz. So the separation here between 500 and 550 when I have a resolution of just a few hertz is great. And I can clearly see that sinc function and clearly see that sinc function. So that's the end of this example. But the real point here is to walk through different cases of the number of samples and how much zero padding they're performing. In general, when you're doing frequency domain analysis of signals, you might not know what signals are there. So being able to play these games, if you have the ability to take more samples, that's always good. If you don't, the data is fixed. You probably want to play with zero padding to increase the number of samples on your underlying curves. And if you're trying to resolve very closely spaced signals in the frequency domain, really the only way to resolve them is to get more data. And we saw that here in this last case, we were actually able to resolve them very nicely because we were able to take 2048 samples. If we were kind of stuck in case 6, there'd really be no way to ever resolve those signals because the width of the sinusoid here blows away the information 550 hertz. So all those are just things to keep in mind when you are doing frequency domain analysis of signals and looking at them in the frequency domain. That's it for now. Thanks for watching.